Welcome back. Now we are going to look at an experiment that I conducted long time back. As some of my earlier experiments with molecular dynamic simulation, I used the SPCE potential, which is simple point charge potential that we discussed earlier by Toucan and Rahman, and I took a number of molecules as 64, created 8 layers of them, and then open in the z direction. So, I said vacuum on the two sides, and I have these 8 layers of ice molecules in a cubic crystal. So, I said that ice also exists in cubic phase. So, cubic ice is now, I created a film of cubic ice, if you may want to think about physically. So, it was periodic on x and y. So, there is a sheet of ice, very long sheet. But then if the length, if you look at the film, is very thin, there are only 8 molecular layers, and each one is presented in the 8 layers. So, the reason we wanted to do, because we wanted to create a surface of ice and see what happens in that case. And then if you look at, we took the 20,000 time steps, which were many picoseconds, and property calculation was done out of this 20,000 step on 10,000, because 10,000 steps, although we started with an equilibrium position of the particles, we again let it go, so that it comes with the right kind of statistics and does not have the initial fluctuations. So, once the system settles down in equilibrium, that is when you start taking the property calculation. So, this is the initial position as you see here, and you can see hexagonal closed system here, but also this is in a cubic formulation. So, this is all cubic ice. So, if you look at, this is a unit cell 1, 2, 3, 4, another 1, 2, 3, 4, and as you formulate them, they are essentially creating a cubic ice system. This is the initial position. So, what I am going to show you property calculation based on what we understood from our correlation function theory, how we calculate some of these at the beginning, that means initial position, and then we let it run for 20,000 time steps and see at the end of the position. So, this is all we are doing. We are not doing anything fancier. We are looking at the initial position, and due to the electronic functions or the potential function, what happens to it. Now, also this is at 0 degrees Kelvin. So, your thinking will be, hey, this temperature is 0 degrees Kelvin, nothing should happen to this layer. It should remain where it is, because it's frozen, although it is a layer. But there are other forces that I want you to observe carefully and see why it is happening. So, this is where what we become is an investigator, molecular dynamics investigator. So, this is a typical way you would do it. Now, if you look at the end of the 20,000, you are seeing that the particles have moved out in various positions. Now, if I can look at this position, and again this is very simple x z plot, you can see that there is smearing of the atom, they are moving around, some of them are intact, some of them have moved out. What can I figure out from here? Not much, because I have not looked at the property calculation. So, position, initial and final positions are important, but what is important now is look at properties. So, now I am looking at the number densities. So, if you look at 1, 2, 3, 4, 5, 6, 7, 8, 9. So, you look at, because it is periodic on x and y, you are seeing these 8 layers. So, the 9th one is essentially the periodicity that is coming back. So, now you can clearly define that the densities of the layers. So, if you look at the densities at the ends of the system is lower than the densities in the middle part of it. So, now you can see that density at the initial point. Now, if you look at after 20,000, you can see that the density has also moved out. Now, if you look at here at the surface, because of the relaxation, there is much more dense system, and then it is 1, 2, 3, 4, 5, 6, 7. So, instead of 8 layers, now it is almost becoming 7 layers system, because the particles have moved out, and I am looking at a particular space between the layers, so that I can find particles in that, and the number density is created here. So, this is just looking at the particle position. Now, we look at G of r, radial distribution function. Remember, we said radial distribution is going out from the central particle, and now we are doing summation on all particles. So, if you look at that, Now, you can see at the initial position is the cubic crystal. So, you can even see how many, this is the first neighbor, second neighbor, third neighbor and fourth neighbor. So, this is all we are looking at in terms of the neighbors from the central atom, and it confirms with the cubic crystal structure. It is very clear that it is a cubic crystal looking at the radial distribution function. And now, if you look at the nearest neighbor, peaks have become wide. That means there are more neighbors now showing up, especially in the second and third neighbor. There is more widening as compared to the first and the fourth neighbor. So, this is what are the things you are looking at. From particle position, it was not clear what is happening here. So, now what we are seeing is that there is a thickening of the layers in between, and if you look at, there is also some thickening of the layer and their coordination number, that means how many atoms each one see has increased. So, that is where radial distribution function. Now, we take the Fourier transform using again similar thing as we did in Green-Cuvo formulation, is that now we are looking at the static structure factor by taking the Fourier transform of that. Now, if you look at the Fourier transform shows the diffraction pattern. So, in a cubic crystal you will see that these are the 4 sites where atoms are being looked at. So, that confirms with the cubic crystal structure at the initial position. But now, pay attention to what happens. Now, these formation which were very much confined to certain places due to the diffraction, and if I would have taken X-ray diffraction of this thin layer, this is what I would see in terms of the average positions of the particle in the system. But here is what is happening in the X-ray diffraction, and in a K space, which is a lattice space that we are looking at, reciprocal lattice space is K, and that is where reciprocal lattice space and how it is smearing out of the lattice spaces. So, we are looking at lots of lattices of 192 particles and the 64 molecules, and we are now looking at the cubic crystal, and when we relax it, what happens. So, this is where now we are looking at the thin film of cubic ice warps and twists, thus becomes deformed over the time of the run, even though at 0 degrees Kelvin. So, the question is that what is causing it. So, even at 0 degrees Kelvin there is a mobility in the molecule. So, now you have to look at 2 ideas, interatomic and intraatomic. So, if you look at intraatomic, mostly if you look at, and we looked at G of R of O and O. So, this G of R was oxygen and oxygen. So, if you look at interatomic. So, interatomic between oxygen and oxygen, the cubic crystal is formed by the heaviest atom. So, you are looking at the oxygen atoms in cubic crystal, and we will talk about different crystals in the coming sections when we talk about stress and strain. But in this case, suffice to say, in this cubic structure there is a movement, a motion of the oxygen atom. So, if you look at here, oxygen atoms within the K space, which is a reciprocal lattice space of the static structure factor, have moved around, and that movement is caused by mostly the electrostatic forces. Because if you look at in terms of the interatomic forces, there are 2 parts of it. One is the Lennard-Jones part of it, which essentially is stabilizing force. So, because of the potential energy well. So, what is left here is the electrostatic force, which is essentially a long range force. So, what is happening due to this particular film is now exposed to vacuum, and so the layers which are at the vacuum are trying to balance the charges. So, in order to balance the charges, is warping and is twisting in order to come to a state where it is going to be essentially a state where it is going to equilibrate. So, there is a widening of G of R peaks, Fourier transform of G R peak, which is static structure factor, also shows significant mobility, and the mobility can be only explained in this case because O and O is Lennard-Jonesian type with different parameters fitted to the Tucan and Raman SPC potential simple point charge. But the Z, which is as you remember, there is a positive charge and negative charge. Positive charge is on hydrogen atoms, negative charge of 0.81 electron volts is on oxygen, 0.41 is on 2 hydrogens, and so if you look at 0.82, which is the double of oxygen, this is how it in a fully electrically satisfied molecule, they both balance out. But because we have now certain bonds which are essentially dangling and open to the surface, this is what causes the warping and the twisting. So, this is how scientists will investigate different phenomena, look at the data, understand it using molecular dynamics calculations, and this is only 192 atoms, 64 particles, molecules, 8 layers, but this is layer by layer calculation. And so, once you take certain number of molecules, you can also do layer by layer calculation and learn a lot about what we do. So, let me stop here, and then we are going to look at some of the advanced properties in the next section. Thank you.